Hi there. Let's look at the new question that I got for thermodynamics. So what I'm having here is let's do the graph for the vaporization for water, but this would be true for any compound or element actually, right? So let's get the y-axis T, the temperature, and x-axis energy. You increase the energy, temperature goes up, and you get a plateau, and temperature goes up, and you get a plateau, and it goes up, right? So we know this is the typical pattern: solid, warm, 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 and you get the solid turns into liquid, and then again water liquid goes into vapor, right? So this graph, yeah, these are the important things: the solid going to liquid and liquid going to vapor. It's an equilibrium. So this is the vaporization portion. So we are given delta H standard and the delta S standard, right? So these values are given, but this could be even in the fusion part too, that is solid in at equilibrium with the liquid water, right? It could be so this one we know theoretically under standard conditions. These temperatures we know, those are boiling points and the melting points standard, right? We know that 100, this is 100, this is 0, but now we are trying to prove it and also make sense of this graph. These heating curves and cooling curves are good things to know for any element. For now, we are focusing on the vaporization of water, liquid to gas, vapor, right? This is an equilibrium. So that's the most important thing to know. So this could be even, aluminum solid and going into aluminum liquid. It's back and forth at the melting point. It's an equilibrium. So that's another example, right? It could be anything. Doesn't really matter to us. So in this case, we're going to use this equilibrium to do the calculation now, right? So be aware of the graph and let's use this formulas. That is delta G delta H is minus T delta S, right? So this is the one we're going to be using because we are given two. We are looking for the delta G. Well, delta G should be 0 at any phase change equilibrium. So that's the other thing to memorize. So phase change equilibrium is 0. So that goes to 0. Then this equation becomes 0 is equal to delta H T delta S, right? Now we can bring the minus T delta S to this side and equals to delta H, minus cancels out. T is delta H over delta S, right? Now we can plug in the values. This is a good way always. So you arrange your formula and then plug in the values. We are given 40.7 kilojoules per mole, the heat of vaporization, and kilojoules we don't deal with. Convert right away. 1 kilojoule is 1000 joules. So you can cancel out the kilojoules, right? Now we also have given the delta S, the entropy change. That is 109.7 joules per k mole. So now the joule to joule we can cancel, right? Kilojoule to kilojoule cancelled out already. Joule to joule cancels out, and then also mole to mole cancels out, right? What is left is Kelvin. So the Kelvin goes up because it's a division here, right? Now we just plug in. Let's see what's the Kelvin value we get. So we are getting 371.01 Kelvin. We know exactly we need to have 300 Celsius, which is 373.15. But given the numbers, this is what we get from the data sheet, right? So be aware of what type of thing we are doing with these numbers. That's the way to solve a problem. So be aware of what is given and have a picture, have a pre-body diagram kind of thing, and then put all the formulas that you think would fit and then do the math right, brackets, right? And then also once you see the final answer, see whether does it make sense, that answer. Okay, we look at the next question. So this is given alkylated cyclohexane, shows two important conformations. With given information, calculate the Gibbs free energy for the forward ring flip, and also comment on the tertiary butylated cyclohexane conformers, right? So now I'm going to just make sense of this cyclohexane ring flips And so that picture will give you a good idea in order to get the delta G calculation, right? So always before you go to the calculation, you should have a little bit of an idea of these things, right? So look at the cyclohexane. This is how you need them later on, right? So the tert-butyl group is the just the hanging one, and then it should be in an equilibrium. And if you can draw this little corner going up, this little corner going down, right? That's how you do understand a ring flip, right? So now the purple area flipped up, the yellow area flipped down, so we get a new chair conformation. It's a new ring flip. Now you see the down tert-butyl group, still down tert-butyl group, but this one is axial and it's like north pole axis, and this one is equatorial. It's just like the equator on the earth, right? So kind of horizontal, that's the equator, equatorial. Now there's another thing. When it is axial, the hydrogen next to the axial group when push away from each other, there's a more repulsion. Theoretically, this should be going to forward. So the ring flip forward theoretically should be around 99%. This side is 1%. That just I'm telling you by experience, by knowing things, but this is a good idea to have this picture in your head, right? Okay, let's look at what is given now. So what is given now is an R group attached and ring flip happens, and it could be equatorial and axial. That's what this is actually the given picture, the green one. Okay, now the question is, what's the delta G value? What's the Gibbs free energy push forward? So the amounts of the first chair is 33%, the other chair is 66%. It could be given in fractions as well, right? Fractions, percentages doesn't really matter. Now, so I'm going to use the fractions just to show you the simple math, but you can plug in the percentage as well. So now the given conditions also in the question is 298 Kelvin and 1 atmospheric pressure. So these are standard conditions. So I'm going to write this standard condition equation, which is delta G is minus RTL and K. K is product over reactants. In this case, product is the right side ring chair, and the reactant is the left side chair, right? Plug in the values. R is 8.3145, 298, Ln 2 by 3 over 1 by 3. These are the molar ratios. Because molar ratios we can just plug in as it is. So simplify the Ln bracket first and times 298, 8.3145, you will get that one. 1717 joules, but maybe it's a good idea to convert to kilojoules. 1 kilojoule is 1000 joules. Divide by that and cancel the joule to joule, you get the kilojoules. So minus 1.72 kilojoules. So this is a negative delta G Gibbs free energy. That means it's spontaneously or more pushing forward, favorable, right? That makes sense because equatorial is preferred. Okay, now the next question. So the based on the above experiment, am I right? Yes. And we have another one, 298 to 398 equilibrium constants are given. Calculate the K2. So let's see. Okay, so this probably, let's see. Yes, so let's see, we can calculate the K2 value. So 298 and 3. So these are the T1 298K, and the K1 is given actually. So yes, K1 is 8.52 and then 398 is given, and the K2 we are looking for. So for this one, we are going to also kind of going to find out is it endothermic or exothermic, just to get the sense of it, right? Now, for this one, yes. So I'm given the delta H value, that is minus 6.2 kilojoules per mole. So we need to convert to the joules. But that one is basically minus value tells me it's exothermic. So we kind of get the sense of how this thing works, right? Now, ln K2 over K1 is equal to minus delta H over R. And inside we have 1 over T2 minus 1 over T1. This is how you do the same reaction, two different temperatures, two different equilibrium constants, right? So that's what we are using now. So 6200 when it's joules per mole, and then plug in the 8.3145 joules per kmol, and plug in the 398 and 298, the T2 and the T1. So we can also deal with the units here, right? And then we should be getting here, if you cancel the joule to joule, mole to mole, you end up with Kelvin here, right? Do I get no, Kelvin also going to cancel out? Yes, we solve the right side, and left side you're going to take the inverse ln. When you take the inverse ln, you're going to look at the e to the power in the other side of the formula, right? So that's how you get rid of the ln, and you look at the e to the power, right? So now your K2 is 8.52. That goes to the right side of the equation, and then you end up with 4.5, right? So that's the value here. So look at this one, 8.5 initially, and then it went to 4.5. Now I'm just going to make sense of what happened. So first round, reactant goes to product, and the T1 goes to T2. In the T2, we got a smaller product, so that's why small p. And in the T1, you got a higher value, that's why p is bigger, product is bigger. So in that case, we should have the heat in the right side, that should be exothermic. We already know that, and that's why, according to Le Chatelier, increment of that gives you those results. Okay, so let's look at the last one, and this is a much simpler one, right? So you can perhaps stop the video and try that. And so in this case, I'm given T1 to 2021 and K1 0.85, T2 3050, K2 9.5, right? I just got like easy numbers to do. And ln K2 over K1 minus delta H over R within brackets 1 over T2 minus 1 over T1. So now we're going to plug in the values, ln 9.5 over 0.85, and then minus delta H over 8.3145, the gas constant, and then plug in the two temperatures, T2 and T1. Now, when you have ln values within the bracket, solve that one. Just plug in the ln within the brackets, the two numbers, you will get the easy number to deal with, right? Now, delta minus delta H we are looking for, and inside the bracket the temperature should be solved first and then divided by the 8.3145, right? Now let's see what happens. We need to isolate the delta H, keep the delta H in your right, and bring the minus 2 10 to the power minus 5 into the left side. So this will give me, yes, minus delta H is equal to minus 1207 10 to the 5. Cancel minus to minus, the delta H is 1.207 10 to the 5. Oh yeah, actually kilojoules 10 to the 2, right? Because you can express normally in kilojoules. So that's how you should do the last question, right? Okay, thank you.